All right, so this is the AASHTO soil classification system by James Norris and Tim Lynch. So, what is the AASHTO soil classification system? Uh, this soil classification system was developed by the American Association of Highway and Transportation Officials. It's widely used in highway and road construction projects, and it classifies soils for suitability as subgrade material. This system categorizes soils based on their grain size distribution, liquid limit, and plasticity index. So, what is the AASHTO system mainly used for? The AASHTO soil classification system is primarily used for evaluating and classifying soils in the context of road and highway construction. Its main purpose is to assess the suitability of soils for use as subgrade materials in pavement structures. Subgrades are the foundation layers of roads and highways, and their performance greatly affects the durability, stability, and overall quality of the pavement. So the key uses of this soil system are first, it's subgrade suitability assessment. The system helps determine how well a soil can support the loads imposed by traffic on roads and highways. Granular soils, which are sands and gravels, are typically preferred for subgrades due to their strength and stability, while silts and clays are less desirable because of their plasticity, and which affects their tendency to shrink or swell. Pavement design and construction. By classifying soils into different groups, engineers can make informed decisions about the type and thickness of pavement layers that are needed for a specific soil type. This helps in designing pavements that can withstand the expected traffic loads and environmental conditions. Material selection for road construction. The classification AASHTO also assists engineers in selecting appropriate materials for road foundations. It helps identify whether the a soil is suitable as a subgrade or needs to be stabilized or replaced with better materials, which will ensure long-term pavement performance. It's also used for soil improvement and stabilization decisions. Soils classified as poor may require stabilization techniques, which will improve their load-bearing capacity. The AASHTO system aids in determining when soil stabilization is necessary. And then last, quality control and specification compliance. Contractors and engineers that use the AASHTO classification system use it to ensure that soils used in road construction meet the project specifications and quality standards set by highway authorities. So the AASHTO system is a very vital tool in pavement engineering, which helps guide the design, construction, and maintenance of durable and stable roadways, which provide a clear framework for soil classification and evaluation. So what are the grain size ranges for each category, and what sieves should be used to define these grain sizes accordingly? So first is gravel, which the gravel has a size range of 75 millimeters to 2 millimeters. And the sieves for gravel, so gravel would be classified as anything that's retained on the number 10 sieve and pass through the 3-inch or 75 millimeter sieve. Next is sand. Its particle size range is 2 millimeters to 0.075 millimeters. And that's anything passing through the number 10 sieve and retained in the number 200 sieve. And there's two different types of sand, which is coarse sand, which is its size is around 2 millimeters to 0.425 millimeters and would be retained in the number 40 sieve. And fine sand, which its size would be 0.425 millimeters to 0.075 millimeters, which would be anything that passed through the number 40 sieve and then retained on the number 200. Next is silt and clay, which these are the fines. Its particle size range is less than 0.075 millimeters, and this would be anything that passes through the number 200 sieve. And then fines, usually their characteristics, silt has a low plasticity, and clay would exhibit high plasticity and cohesive properties. And the classification groups for the system. So these soils are classified into 7 major groups, which are A1 through A7. Each of these have subgroups, and the main groups are first A1, which is well-graded granular soils. These are good quality materials for subgrade use, typically sands and gravels. Soils under A1 include well-graded sand, gravel, or a mix of sand, silt, and clay. Their subgroups are A1-A, which are gravelly soils, and A1-B, primarily sandy soils. Next is A2, which is granular materials with fines. This group includes a variety of soils from coarse grained to fine grained, and they have some silt and clay content. These A2 soils are generally suitable for subgrade materials, and their subgroups are A24, A25, A26, and A27. The subgroups depend on the silt and clay content. Next is the A3, which is fine sand. These are primarily clean, fine sands or sands with silt in them, and they have a limited clay content. A3 soils are typically really good subgrade materials, but they lose stability in wet conditions. Next is A4, which are silty soils. These soils have a high silt content with little to no plasticity. They're not as desirable as A1 or A2 soils for subgrade because they also lose strength when they're wet. Next is A5, which is high liquid limit silty soils. Soils that have a high liquid limit, which would be a value greater than 40, are often fine silts. They exhibit poor performance when wet due to the high water sensitivity and swelling and swelling potential. Next is A6, which is clay-like soils. These are soils with high clay content and a low to moderate liquid limit, which would be below 40. They're more plastic and less suitable for subgrade because they expand when they're wet and then they shrink when they're dry. Finally is A7, which is clay-like soils with high plasticity. Soils with high clay content and a high liquid limit, which is would be a value greater than 40. These soils, which are particularly the subgroups A75 and A76, have poor subgrade performance due to their high shrinking and swelling behavior. And then for finer soil classifications, which would be A4 through A7, the group index would be needed, which would provide a further evaluation. So the group index is a numerical value that's calculated based on liquid limit, plasticity index, and the percentage passing through the number 200 sieve. A higher group index value indicates poor suitability as a subgrade material. So this is the formula for calculating group index, where F sub 200 would be the percentage passing the number 200 sieve, LL is liquid limit, and PI is plasticity index. All right, so what is the importance of AASHTO sieve analysis? AASHTO sieve analysis is critically important in civil engineering, particularly in the context of road and highway construction, because it provides a systematic method to determine the grain size distribution of soils. The results of this analysis can help engineers understand the physical properties of the soil, as well as assess its suitability for various applications, particularly as subgrade material in pavement structures. So here are a few key reasons why AASHTO sieve analysis is important. One, determining soil classification. Sieve analysis is the primary method used to categorize soils within the AASHTO soil classification system. And by separating these soils into different sizes, the analysis can help classify the soil into one of AASHTO's groups, which is crucial for determining the soil's properties. Two, evaluating soil suitability for subgrade. Subgrade performance directly impacts the long-term stability and strength of pavement system. So sieve analysis can help engineers evaluate whether the soil is granular or contains a large amount of fines, which tend to weaken the subgrade when wet. Three, grain size distribution for material selection. The gradation of soil particles, whether the soil is well graded or poorly graded, will affect the soil's load-bearing capacity and its different characteristics. So well-graded soils are usually stronger and more stable for construction purposes, while poorly graded soils need more stabilization. For pavement design, the grain size distribution revealed by sieve analysis can help engineers design pavement structure. Five, predicting drainage behavior. Coarse grain soils will allow water to drain more easily, which is a more desirable property in subgrades. So it's important to be able to predict this behavior. Six, soil stabilization decisions. Sieve analysis results can guide decisions on soil stabilization methods, which can help identify stabilization techniques when it's necessary. And then seven, quality control and construction. During the construction phase, sieve analysis is important for ensuring that materials used for designing roads and highways are able to meet specifications.
Okay, so other parameters used to define soil type. You have effective size, which is D10, the uniformity of coefficient Cu, which is equal to D60 divided by D10. You have the coefficient of gradation, Cc, which is D30 squared divided by D60 times D10. All of these items can be determined from a particle size distribution curve created from sieve analysis and hydrometer analysis, ASTM D422. Having this graph can help you determine the following: whether it's poorly graded, which will be curve 1 on the graph I show you next, well graded, which will be curve 2, and gap graded, which will be curve 3. Now, if we look at the graph, you can see curve 1 is poorly graded, as it has most of its material in 1 or 2 areas. So there's no uniformity. It's either really big or really small. Well graded shows a very uniform curve. This shows that there's a very equal distribution of granular sizes. And gap graded shows you that there are 2 or more different areas of condensed particle size. The other differences between the systems are the particle sizes themselves, as you can see from the graph. The gravel differs among them. AASHTO is 2 millimeters to 76.2 millimeter grain size. USCS is 4.75 to 76.2. And USDA is anything greater than 2 millimeter. Sand, again, we have different sizes. 0.075 millimeter to 2 millimeter for AASHTO, 0.05 millimeter to 2 millimeter for USDA, and 0.075 to 4.75 millimeter for USCS. Silt and clay differ among them. AASHTO and USDA have different classifications for silt and clay. You can see the digits here. The only difference is the larger size. USCS, however, defines no separation and call the combination fines, and those sizes are less than 0.075 grain size. They also have different classification tables. As you will see, I have all 3 of them, 2 on the next slide. AASHTO has A1 through A7, and then they have various subsets depending on the sieve analysis and the characteristics of the soil type. Now, it's also worth mentioning that AASHTO used to have A8, which qualified as peat. And peat is a very organic clay type silt, which means there's a lot of organic material mixed in. For UCS and USDA, USCS has major divisions, with your coarse and your fine grained soils. And they furthermore divide them into gravels, sands, silts, and clays. They have their lettering system, which you can see the group symbol. GW is a well graded gravel, SW well graded sand. You can see at the bottom of the table, it tells you what the prefixes are: G for sand, or G for gravel, S for sand, M for silt, C for clay. And then the suffix well graded, poorly graded, silty, clay. Over on the USDA side, they use a triangle system based on the percentage of the material in the sieve analysis. So depending on your percent passed, you can go to this and determine whether you have a loam, a clay, silt, or sand. For example, if 40% clay passed, 30% silt, and 30% sand, you would go to your 30 here, come down to your 30 line, and you meet your 40. So that would be a cross between clay and clay loam. Again, the systems have their specialties, where AASHTO is preferred for traffic, highway construction, transportation. USCS is preferred by the geotechnical engineers when they're designing their jobs, and the USDA is mostly used for agriculture. Thank you.